Hi friends, today we start lecture 45 on our helicopter dynamics course, and today I'm going to discuss the lag equation, and specifically we are going to focus on the right hand side of this equation looking at the forcing term. I'm Dr. Anjan Ganguly. Now let's go back and think about the lag equation which we have derived some time ago. Now if you recall, there was the term zeta double star plus nu zeta square into zeta, where nu zeta is the non-dimensional lag frequency. And then on the right hand side we had the forcing term f zeta, and the integral here is from e to r. So this we had called as gamma m beta bar. So we are going to look at this right hand side of the equation and get an expression for this term using BET so that we can write out this equation for vertical flight. So let's look at this equation and try to get something for f zeta. Now immediately you realize that f zeta, which is the force in the in-plane direction, is going to be equal to f of x. And f of x has essentially two components. One of them is the drag, which is essentially coming from CD, or the airfoil cross section. And one more component is due to the component of lift, which is pointing in the backward direction, that is lift into phi. Okay, this is the induced drag type of component. So now we write this expression using our usual formulas for lift and drag. You remember them: half rho u square CDC. And again we have the approximation here that u is approximately equal to ut. Phi is given by up by ut. So here you have phi here, you have phi here also. So we simplify this or expand this out and we get this expression here: half rho Ca theta up ut minus up square plus the drag term here. So this term is essentially a lift term because you can see the presence of A here, A being the lift curve slope, and this is a drag term because you have CD naught here, which is coming from the section you are at. This is the profile drag type of component. So in vertical flight, we have ut is rotation speed into r at a given station at which you are at right now, and up is going to be capital V plus small v, where capital V is the climb velocity, small v is the induced velocity at the rotor disk. So this is expressed as lambda into rotation speed into radius. So we put these two expressions into our previously derived expression for f zeta, and we can expand it out in this form and further expand it out in this form here. Now we will assume lambda is constant so that some of these integrals become less difficult to find, and then we look at the integral e to r f zeta r minus e dr. So we take the f zeta term, put it here, and multiply it by r minus e dr, and then integrate it from e to r. Okay, and we will assume theta is theta 0 plus r theta tw, so we can directly look at the effect of the twisted blade. And if you do not like twist, then simply set theta tw to be 0 and you will get that expression. So now the problem is essentially a mathematical problem. So we can perform these calculations here. So we take each of these terms, we split them out separately, and then we take a look at each of these terms and see what are the possible terms which are functions of r and what are the terms which are essentially constants, and then we drag those constant terms out of this integral sign. So we will assume here that chord is constant, a is constant, and of course theta 0 can be brought out, lambda is constant, and so then the integrals are obtained as follows. Now here you will see that there are two basic type of integrals. One is the term involving r into r minus e, and the second is the term involving r square into r minus e. So we are going to find these two integrals next. So let's look at the first term, r into r minus e. So again, this is quite simple. You expand this out. Remember, r square becomes r cubed by 3 and re becomes r square e by 2. And so you calculate this from the bounds e to r. So you get this expression here. You simplify it, you get this expression here. Okay, so that's how we get the first integral term. Now for the second integral term, that is again r square into r minus e, we again expand this out in this manner. So you get r cube minus r square e. This becomes r4 by 4 minus r cube by 3 into e to r, and then expand this out. You get this form here. So again, these are all going to be numbers in the end, because r is the blade radius, which you know, e is the distance of the lag hinge from the root, which you know. So essentially, once you plug those, these are simply numbers. So we can now write the right hand side moment, that is gamma m zeta bar, in this form here. Okay, so what I have done here, I have taken this term 1 by I zeta into rotation square, and then the integral term which we have calculated before, I have put that entire term here. Okay, so you have a pretty cumbersome looking expression here, but you will realize that all these values are in fact known for a given rotor blade. Now of course, lambda would have to be calculated using momentum theory, and density of air is known, the chord of the blade would be known, the lift curve slope would be known, and theta 0, theta tw would be known, and CD0 again is known from the airfoil cross section. So if you have all this information, you can calculate all these terms and you will know what is the right hand side, and in this case it is simply a constant. So let's finally get back to the equation. So what we have done here is, we had the left hand side of the equation from before. We know what is the genesis of these terms, the stiffness term particularly, and now we also obtained the right hand side using BET. So that's the right hand side equation. Looks quite cumbersome, but now we have a good and closed form expression for this right hand side. And so once you calculate lambda using momentum theory, you can get this term, and therefore you can solve this equation and see what is the solution of this particular equation in the vertical flight condition. So remember that these are looking at vertical flight conditions. Later we are going to look at forward flight. But vertical flight gives you a good picture about many of these things, and the equations are very simple to solve by hand. So very often you can use these hover and vertical flight type of solutions as benchmark solutions, which can be used to compare the prediction of comprehensive codes. So very often in the industry, comprehensive codes are used to actually calculate for the lag response, flap response, and so on. But these codes should give you results which are similar to the ones these equations give you for the particular flight conditions you are at, and presuming some of these things, for example, lambda is constant and so on. So that's one of the good points about knowing these closed form solutions, is you can check the veracity of the complicated mathematical models in the extreme cases or in the bounding cases. So I will end this lecture today, and in the next lecture we are going to look at the third motion, which is the pitch motion. See you then.